Thank you very much for the invitation, for the introduction. I'm very excited to be here. So before I begin, I feel obliged to remind everyone that the Russian invasion of Ukraine is continuing, and I think it's important that we stay aware of the atrocities that Russian army is committing, and I'd like to encourage everyone to be on the lookout for opportunities to help Ukrainian people. So what I'm going to talk about is revolving around the following notion. So let me start by stating it in the maximal generality. So let's say that T is any scheme, and I'll fix a prime number which will be invertible on that scheme. So here is the central definition. So I'll say that a QP local system L on the scheme T, well, in the étale local, in the sense of an étale local system, is of geometric origin. If it comes from the relative cohomology of a family of varieties, and the precise notion is that I'll allow myself to restrict to a dense open such that there exists a smooth proper family over that dense open. Such that the restriction of L to U is a subquotient of the cohomology local system of that family in some degree, and possibly twisted by some powerless economic character. And I'm including this twist to make this class of local systems stable under duality, so that J might be positive. Okay? So kind of the central question, which I'm personally very interested in, is the question of classification of all local systems of geometric origin. And this somehow is the most, I guess, most studied in the particular case where T is just a point. It's the spectrum of a number field. So let's say that F is some finite extension of T. So then there is a precise expectation for so for what are the local systems coming from geometry, and here, well, local systems on that scheme are just representations of the Galois group. And my notation for the Galois group will be GF. So the expectation is the Fontaine-Mazur conjecture. I'll call it conjecture A because there will be a complementary conjecture. So just for simplicity, let me restrict to the irreducible case. So an irreducible representation of the Galois group on a QP vector space is of geometric origin. If and only if the two conditions are satisfied. First one is that V is almost everywhere unramified. So at almost every place of F, the inertia subgroup acts trivially. And the second one is the condition at P, where P is this prime, is that for every place above P, the restriction to the decomposition group at that place is a drum representation. So these conditions are necessary if your V appears as a subquotient of the cohomology of a variety. So the only if direction is known, and the challenge is to prove the converse. So my first main point will be to contrast this conjecture with what happens if I look at a slightly different example of a T. So let me rather look at the following example of another T. So let's say that I start with some smooth variety over that number field. And let's say that as my scheme T, I'll take the base change of S to F bar. So it's a variety over an algebraically closed field. Well, in that case, local systems is a purely topological notion, right? So local systems on SF bar are just the same as, well, if I were to fix a base point, and let me just, for simplicity of what will come after, I assume that my base point is defined over F. Local systems are the same as representations of the fundamental group of y1 et al. Of SF bar, which, since this is a scheme over an algebraically closed field in characteristic 0, this is the same as the profinite completion of the topological fundamental group if I were to choose an embedding of my base field into C. Okay, so this is a purely topological notion. Well, I'm looking at continuous representation. And the question is, so can I characterize local systems of geometric origin on that variety? I'd like to state the following conjecture. And one of the main points of my talk will be try to advocate for this conjecture. So yeah, I'm not quite sure who to attribute it to. I think definitely Daniel Litt has believed in this conjecture for a while. So conjecture is that a semi-simple local system L on SF bar is of geometric origin. If and only if L extends to a local system on S itself will possibly extend it to some finite extension of F. So for some finite extension F prime over F. Okay? So the forward direction is quite clear. If your local system on this variety over an algebraically closed field came from geometry, then the family which gave rise to it can be descended to some finite extension, and therefore Ital cohomology produces for you such a descent. And what this conjecture is claiming is that the converse is true. If you started with some local system and you've managed to extend it to the arithmetic fundamental group over some F prime, then your local system should come from geometry. So you might notice kind of a jarring discrepancy between these two conjectures, and it seems that I should be obliged to kind of add here that this extension to F prime should at least satisfy the assumptions of the Fontaine-Mazur conjecture, for this conjecture B to at least have a chance at being true. But one of the main points which I want to make is that this is not necessary. And because of that, well, I'll try to say a little more. I think that conjecture B might be more accessible than conjecture A. So the main result which please, yeah.
Just a very small question.
Please.
So in your definition of geometric origin, you work with local system of a given way because you have certain I and J and not direct sample different I and J. So of course the way disappears when you pass something you cannot define it over algebraic closure, but still suppose you start from something which is something which appears in even cohomology and then something which appears in odd cohomology.
Sure, okay.
What happens, and then this is semi-simple.
Okay. Thank you very much. Thank you. Thank you. I think this should be better. Thank you. Yes. Yes, this is very good. Great. Right. So yeah, what will contribute to the evidence for this conjecture, which at least now hopefully not obviously false? Well, so the first theorem is as follows. So this will be a purely local result. I'll work over a p-adic field. So let's say that K is a finite extension of QP, and X over K is a space variety. So let me kind of state two parts, which will sort of hopefully will make this a little more understandable. So if you have a local system L on X, which is a QP bar local system, it's somewhat important here to work with algebraically close coefficients. Such that, well, now this is living over X, right? So it's a representation of the arithmetic fundamental grid. Such that if I restrict it to a local system on the base change of X to K bar, this becomes irreducible. Then there exists a character of the Galois group of that p-adic field, such that if I twist this local system by a character, it becomes the Rhamness. In particular, all of its stalks at K points are the Galois represented. And note that this twisting doesn't change the underlying local system over K bar, right? Because this is just a character of the Galois. So another way to put this is that if I started doing an arbitrary local system on X, then I can find another extension of the corresponding local system over xk bar to X, which is the Rhamness. Okay? So in that sense, the Rhamness condition is automatically guaranteed if you choose your extension appropriately. Like, of course, without this twist, it would be false, because you can find even non-Rhamness characters over a point. And let me just complement this with a statement which works for not necessarily irreducible local systems, well, not necessarily geometrically irreducible ones, which is that for any, well, here you might as well work with QP local systems. For any QP local system L on X, there exists a Rhamness local system M, such that if you go to K bar, L is contained in M. Can be embedded into M. So without this geometric reducibility assumption, it's a slightly weaker statement. And let me just remark that I don't know if we can always achieve the situation where this map is an isomorphism in general. If you can literally just change the extension of a given local system to X over K. So I think for non-semi-simple local systems, there is an abstraction to doing so, which you can write down, but I don't know examples where it's non-zero. Particularly, I'll be happy to hear any thoughts.
Can I ask this
please, yeah.
small question? On the previous blackboard, there is still a tiny point which is not, so on this supposedly easy part of the conjecture B. So you say that if something is of geometric origin over SF bar, then it extends to a local system on SF prime.
Mm-hmm.
Now, if it is a sub-quotient, then how does it descend to something which is still a sub-quotient in the sense of local system over F prime? Because then you have a contribution of the finite of the Galois group of
this requires an argument, yeah. If you have, well, yes, so somehow if it's a subquotient, then I might have to, even if I've managed to descend my family of varieties to F prime, I might have to further extend F prime for that particular subquotient to be stabilized by the Galois group. And then I might further need to extend it to go from the character of this representation of the fundamental group being fixed by the Galois group to the actual representation being fixed to kill some element in the Brouwer group. There's an argument needed, you're right. But I think this is a true statement. Indeed, it would be more obvious if my condition was that L is equal to all of the cohomology. That's good. Mm-hmm. Yeah, any other questions about what I said so far? All right, so the point of this is the corollary that says that if we again go back to the number field situation, and I'll try to denote schemes over number field by S, and everything that's happening locally will happen over some variety X. So if L is well, any local system on S, then there exists another local system M such that the geometric monodromy of L embeds into that of M, and the stalks of M satisfy the assumptions of the Fontaine-Mazur conjecture. So these conditions 1 and 2. And for every, say, point in a values in a finite extension, the stalk at S satisfies as a representation of the Galois group of F prime, satisfies 1 and 2. Okay. So the reason is that well, I guess second part of this theorem takes care of the Theorem condition and the fact that you can always arrange for that larger local system to be almost everywhere unramified. This is a quick consequence of the results on the specialization of the fundamental group, meaning that the Galois action is unramified and on the appropriate completion of the fundamental. Okay. So, and this is, well, I think this is an evidence that if you believe the Fontaine-Mazur conjecture, you should as well believe conjecture B, because it tells you that if you have some arbitrary extension of L to SF prime, you can always modify it so that the stalks will be, assuming the Fontaine-Mazur conjecture will be of geometric origin. Okay. Now, I think kind of the merit of looking at the conjecture B separately is that I think it's totally plausible that the conjecture B might be proven before conjecture A is proven. And let me just, to put this into context, let me remind you what we already know about conjecture B. So let me get another board. Sounds good, yeah. Please, yeah. No, that's the point. It's not Galois covariant. If it was, then I think, well, L would be forced to be the Rhamness if it was a sublocal system. That's the point. Yeah. Exactly. Yeah. So let me say what it's known about conjecture B. So just kind of as a warm-up, let me say what happens in rank 1. So if your local system is of rank 1, you can prove that L extends to SF prime for some F prime, if and only if L has finite monodromy. So it's a character of finite order. And the reason for that is wave conjectures. Well, indeed, if you have a representation of the fundamental group over F bar into, say, QP cross, which happen to extend to a representation of the fundamental group to the arithmetic fundamental group, then, well, since this is an abelian group, it moreover factors for the abelianization of that group. But this is the semi-direct product of the Galois group and the fundamental group over the RGPL closure abelianized. But it means that if I look at the abelianization, it will be the abelianization of the Galois group and the product of the abelianization of the topological fundamental group, or I guess geometric fundamental group, but also quotiented by the action of GF. So I'm taking co-invariance of GF. And now, because the action of the Galois group on the first cohomology, well, the action of Frobenius elements has weights which has eigenvalues which are different from 1, this is a finite group. So it means that the homomorphism from that group factor through a finite grid if I have this condition about being descendable to SF prime. So you see that the rank 1 case is true, and it follows from a kind of piece of characteristic P geometry. And I think it might be instructive to compare this with the conjecture A, where rank 1 case is also known, but it's a completely different part of number theory. It's a consequence of class field theory. Okay. Now, I guess maybe a more serious evidence towards conjecture B is that the analog of conjecture B is true and it's known if you replace F by a finite field. And if you assume that S is a curve. And this is a consequence of the Langlands correspondence, or I guess the proof of the Langlands correspondence over function fields in characteristic P. So this is the work of Drenfeld and Laforgue. Because what they prove is that if you have a local system, say an irreducible local system over a curve on a curve of a finite field whose determinant is finite, then they find that local system in the cohomology of a Stuka space. In particular, it comes from geometry, right? And there is some progress towards conjecture B, say in the rank 2 case, due to Snowden and Zimmerman, which relies on these results in characteristic B, and which proceeds by sort of lifting this from characteristic P to characteristic 0. But I think in general, it's not so clear how helpful this result when applied to the number field case. Right? Yeah. So this is some another. I think this is the status of the conjecture. So my main goal today will be to sketch a proof of at least first part of Theorem 1. But before I do so, let me put it into context by restating it slightly. So I think I'll erase the Fontaine-Mazer conjecture. And please do ask any questions if something comes up. Please.
The rank 1?
Yeah. That's a great question. In general, as stated, this is false. For instance, if you took a Tate elliptic curve, then I think there is a rank 1 local system with infinite monodromy. I'm saying that there are ones which extend to the arithmetic fundamental group and still have infinite monodromy. Because I think for a Tate elliptic curve.
I agree that I understand that.
Right, but I think it should be the ones which come from geometry, you mean, or I think the ones which come from geometry should still be those which have finite monodromy, because for a p-adic field you can still apply Hodge theory if you choose an embedding of QP into C. And for instance, the existence of a polarized integral Hodge structure forces anything of rank 1 to be of finite monodromy. Yeah, for rank 1, in the rank 1 case, everything is fairly explicit. It just comes down to the action of the Galois group on first cohomology. This is the. But yeah, it's a good point. So somehow the analog of conjecture B over local fields, it's definitely false. So the local Galois group is not enough in general. There could be some versions where you maybe additionally assume that you're crystalline, but I don't want to state anything precise. Okay. Right. So you see that somehow in Theorem 1, I was trying to kind of somehow the primary object is a local system over xk bar, and I was really choosing an extension of it to x over k. And there is a very convenient kind of machinery for working with that, which I learned of it from Sacha Belinson, and it somehow it basically uses a Tanakian perspective, and I think it's quite helpful for thinking about these questions. So I said that the fact that in corollary 1, the almost everywhere ramifiedness condition can be satisfied as a consequence of the properties of the Galois action on the fundamental group. And it's natural to kind of ask whether theorem 1 has some reflection in terms of the action of the Galois group on the fundamental group. And well, it does, well, in a sense, in a tautological way. So let me set this up. I'll need one particular notion that is of the pro-algebraic completion. So if you have any group gamma, which might also carry a topology, so let's say a topological group, then I'll denote by gamma pro-algebraic an affine group scheme over QP, which is characterized by the following universal property, such that there is a map from the group gamma to the QP points of that group scheme, which is, well, continuous, such that whenever you have a representation of gamma into a linear algebraic group, so I might as well assume that it goes to some GLN, well, which is continuous. So for every continuous representation of rho, there exists a unique homomorphism of group schemes from gamma pro-algebraic to the corresponding algebraic group, such that if I take the, if I restrict the algebraic to QP points, the diagram will be commutative. So basically, it's a group scheme which completely captures the representation theory of gamma. But it forgets everything about kind of the part of gamma which is not visible under linear representations. Or in other words, like if you prefer the Tanakian perspective, this gamma pro-algebraic is the Tanakian fundamental group of the category of continuous representations of gamma. Okay? And I'll apply this construction to the fundamental group. So let me just, for brevity, denote by pi1 pro-alg. So let me just state this in the local setup. The pro-algebraic completion of the tau fundamental group. Okay. Now, well, if my x is a rational point, then this has an action of the Galois group, and just by functionality, this group scheme gets an action of the Galois group. And you can restate theorem 1 as follows. So let me frame this as a corollary. The first one is that the first part is that the section is the Ram in the appropriate sense. So what exactly do I mean by this? Well, this is an affine group scheme, so it's completely captured by its ring of functions. And you can phrase this as saying that for any finite dimensional subrepresentation of that ring of functions, which is being acted on by the Galois group, so this is finite dimensional. This is a Ram representation. Yeah, that's what I want. Well, in particular, if you have anything which is a quotient of a finite dimensional subrepresentation, I'll also know that it's Ram. But I don't know anything about weird finite dimensional subquotients which are quotients of an infinite dimensional subrepresentation. I don't even know if those exist. Yeah. Right. So I'm saying that some of this, the Galois action here actually might not be locally finite, and it's almost never is. But I'm saying that the Rhamness property holds for the union of finite dimensional subrepresentations. Okay. And well, in the global case, you can just say that if I had a variety S over smooth variety S over a number of tilde F, then for any finite dimensional sub-representation of the ring of functions on the pro-algebraic fundamental group.
Sorry, so there is no irrigation.
There isn't, yeah, exactly. Well, this A corresponds to part B in theorem 1. And this is almost it's quite straightforward to go from B to A. Well, I'm not sure if I'll have time to say this, but it doesn't require any additional input. Yeah, so I can just complement this with a statement about the action of the global Galois group. So any such finite dimensional V which is stable under the Galois group satisfies the assumptions of the Fontaine-Mazur conjecture. assumptions of the contained Maser conjecture. Okay. So in this way, you can view these functions on the algebraic fundamental group as a source of representations against which to test the Fontaine-Maser conjecture. Of course, I'm sort of cheating slightly because it's not so easy to come up with explicit examples here. Because, well, this is, well, right, because we don't, so somehow if you choose, probably if you choose a random vector here, most likely its Galois orbit will be infinite dimension. But it's sort of, it's an interesting but a somewhat separate topic of coming up with representation, which is related to kind of coming up with test objects for conjecture B. All right. And so, yeah, I don't want to say much about how this corollary follows, but let me just assert that this really doesn't require any additional work. Basically, you use that functions here can be thought of as matrix coefficients of representations, which correspond to locals. All right. Now, well, maybe just to put this into context a bit more, let me compare this to something which is probably more familiar. So, corollary 2 is quite well known. So, mark for, and again, I'm sorry, I don't quite know what the precise reference is. It's probably somehow implicitly contained in Deline's text about P1 minus 3 points. For the pro-unipotent completion instead of the pro-algebraic completion. And the reason is sort of the best possible one, which is that you can rewrite the space. Yeah, so pro-unipotent completion is just something where it's defined by the same universal property, but I'm only ranging over representations which factor through strictly hypertriangular matrices. So those which are extensions of trivial representation. Because this is essentially Italc homology of a scheme. This is the zero of Italc homology of a certain co-simplicial scheme, which I suggestively denote as the loop space. So somehow, whatever proof of the fact that the Galois action on the Italc homology is Theorem you prefer, it should carry over to co-simplicial schemes. So this is a scheme. So in a sense, kind of this space basically comes from geometry in the sense I stated above, except that, well, here the interesting part of the action is the non-semi-simple part. But yeah, I just want to mention this to highlight that the proof of corollary 2, which I have, which goes through theorem 1, is really not of this form. It would be very nice to kind of explain explicitly how this functions of the pro-algebraic completion related to the Italc homology of some variety, but that would basically constitute proving conjecture B. So really, the proof will go through some abstract p-adic sphere. Right? So having said that, this is kind of a source of representations which satisfy the assumptions of the Fontaine-Maser conjecture, it might be kind of curious to ask how rich this source is. Yeah, so let me state a theorem which maybe I'll get a chance to say a few words about the proof of. So basically, it says that the source is as rich as it could be. So if you take any representation of geometric origin, so every, well, let me assume semi-simplicity, semi-simple representation of the Galois group of the number field of geometric origin, is a subquotient of the space of functions on the pro-algebraic fundamental group of one particular variety. And this variety is just a projective line with 3 punctures. And I have to work with a tangential base point, but this is largely an artifact of the proof. So this is a tangential base point. Okay, So it can be proven that if you take anything which appears in the cohomology of some variety, you can then find it as a subquotient in this space, well, compatible with the Galois action. Okay? And this is sort of, I guess, maybe an indirect indication that these algebraic completions, they usually behave quite wild as soon as your group kind of is, has enough representation. So here, the group in question is just the profile completion of the free group into generators. And so in particular, well, its algebraic completion is something huge. Right? So are there any questions about what I said? This is a number field. Yeah, this is crucial. Sorry. So F is a number field. Yeah, the proof relies on Bailey's theorem, so it crucially uses a number field. Yeah, thank you. So I'll try to stick to the convention that F is a number field and K is a p-adic. Right. So before I move to saying a few words about the proof of Theorem 1, let me just collect these results together. That is of Corollary 2 and Theorem 2. So somehow I've mentioned 3 classes of Galois representations. We had representations of geometric origin. And Theorem 2 says that any such representation, so let me assume semi-simplicity from the beginning, is a subquotient of this huge vector space with an action of the Galois group. And somehow I didn't state this in Theorem 2, but in fact you can print it as a subquotient of the Galois finite part. There's a part where every vector has a finite dimensional orbit. So, and again, well, surely semi-simple subquotients. And now Corollary 2 says that every such subrepresentation, such subquotient, satisfies the assumptions of the Fontaine-Maser conjecture. So semi-simple representations satisfying the assumptions of the Fontaine-Maser of the. Okay, so this is Corollary 2. This is Theorem 2. But of course, if we believe the Fontaine-Maser conjecture, we do believe that this class is just equal to that class. So both of those inclusions should be equalities. So yeah, let me just put it on the board. Inclusions are equalities. But I don't quite know how to prove either of those things. So proving that this is equality is intimately related to proving conjecture B, and well, this is something else. Right. So I don't. Maybe I should apologize for drawing this cartoon. I don't know if it's immensely helpful for approaching Fontaine-Maser conjecture, but I just found it curious. Right. So let me move to p-adic Hodge theory, and I'll sketch a proof of Theorem 1. So, but are there any questions? Okay, great. So, and I'll concentrate on the first part of Theorem 1. So, suppose you start with an arbitrary local system on a variety over a p-adic field. And well, I know it's geometrically reducible, and I'm trying to find this character such that the twist will be de Rham. But yeah, well, de Rham by definition is the fact that applying certain functor gives you a large enough object. But well, what do you do if you start an arbitrary representation? It would be very useful if there was some sort of invariant or I don't know, invariant attached to all local systems, which would remember enough information so that then the de Rham property could be read off this invariant. Unfortunately, there is such a thing. So the key input into theorem 1 is the p-adic Riemann-Hilbert correspondence, or I should say a p-adic Riemann-Hilbert correspondence. Yes. So this is a combination of works of many people. Let me just mention, well, the particular version which I'm going to use. It's sort of due to Diao Lan Lionju, but it sort of rests on some of the previous work of Scholze. And well, somehow the way of stating it in the case of a point, which, if I understand correctly, was invented by Jean-Marc Fontaine. And in particular, I also need a decompleted version, which is due to Koji Shimizu. But again, this is definitely not kind of a complete list of people who contributed to these ideas. Right. So here is the statement. And this will also be an opportunity to remind you what a de Rham local system is. So my setup is that I have a finite extension of QP, and I have a smooth variety over it. And I'll try, this will be a functor from QP local systems on X without any further conditions. And it will go to a certain category of de Rham flavor. It will be some modules with connection. And the field of coefficients there will be an extension of K obtained by adjoining all p-power roots of unity. Okay, but I'm not completing it, so it's an infinite algebraic extension. So the target category of the function, which I'll call RH plus, and it will be in a second clear what plus stands for, is the category of vector bundles on the base change of this variety to K infinity, where I additionally adjoin another formal variable. So you can think of it as a kind of formal scheme, which is a trivial formal one-dimensional thickening of xk infinity. And let me introduce a letter for this vector bundle, which are equipped with a connection. So with K infinity linear flat connection. Which is allowed to have poles along t equal to 0 of order at most 1. So this is a nabla is a map from E to E tensor differential forms with possibly a logarithmic pole. Okay. So this is the kind of object which you get, and let me just introduce some notation for this category, which is kind of made up, but it's vector bundles on xk infinity adjoin t. With a logarithmic connection. So noted by nabla log. Right? And the crucial point is that this functor is faithful. So it reduces injection homomorphism. And it's also monoid. So for instance, it preserves ranks of objects. So a local system of a given rank is being carried to a vector bundle of the same rank. Right? So how is that related to de Rham local systems? So you can recover the result of applying d de Rham to a local system from RH plus up to a slight emission. So there's a function from here to just vector bundles on xk infinity. So now without this additional thickening, which sends E to the following. So you can invert T. So then you're getting something over the Laurent series in T. So in particular, this is just a genuine connection because the poles don't matter anymore. And you should take the flat sections with respect to the derivative in this T direction. So you're going to get a sheaf on xk infinity. Okay? And this functor is not faithful anymore because there might be vector bundles which well, such that the connection on this formal punctured disk is not trivial enough, so it doesn't have enough flat section. And this composite functor is the functor d de Rham, well, but with scalars extended to K. Okay. And well, if you like, you can take this as a definition of the de-Rham. So let me say a couple of things about the properties here. So please. No, it's not completed. Yeah. Somehow. Yeah. It's basically this k infinity of t is the decompletion of b de Rham applied to the completion of that field, which is a perfectoid. Right, and this is the Cauchy's distribution. That's in Cauchy's paper. And like, he needed to do a little bit of work to make this global. He did it locally, but substantially this is Cauchy's. So this is differential forms on this formal scheme, including differential forms in the t direction. But I'm also allowing poles of order 1 in t. So this is 1 over t. So let me try to write this more legibly.
You allow to divide by t only differentiation in the t direction, or also differentiation in the other direction?
Well, in fact, it lands in the category where I only divide by t the differentiation in the t direction, but I might as well state it like that. Yeah, but it's true that you actually land in a category where only along in the horizontal direction you have poles. That's a good point. Thank you. Any other questions? When I take bracket, I might have to divide by t squared. True, yeah. Yeah. Well, I think maybe just to make this less confusing, I should do this, but I think anyway, RH plus lands in the subcategory of only poles. I think this is a legitimate notion, but maybe not very useful. Okay. Any other questions? Okay, great. Yeah, so let me say something about these functors. So depending on how you prefer to think about various functors in p-adic Hodge theory, it might be useful to indicate where the Sen operator here is. So if you take t and multiply it by the derivation in the t direction, then this will be the what's in some other approach, well, what's sometimes called Sen operator. Well, again, or maybe in this setting, I should rather call it Fontaine-Sen operator. Sure, well, it depends on where it acts for. If you want to act on Hodge state cohomology, it will be mod t. But I think, didn't Fontaine also had like a version over the series in t in his paper about arithmetic of p-adic representation? Okay, my bad. Okay, sorry. Thank you, yeah. Okay, so this is just to compare it. So let me tell you what this functor does in a very simple case, because it will be somewhat important for later. So if you just have a point, then suppose you have, then your local systems are just representations of the Galois group. So suppose that your representation is a power of this economic character, where A, say, is some p-adic number. Well, such that it makes sense to raise this economic character to that power. Then RH plus of this character is equal to, well, it's a rank 1 module, so it's k infinity of t, where the connection is, well, the de Rham differential plus dt over t multiplied by a. Now, in general, your local system is de Rham. Well, by definition, L is de Rham. If and only if the result of applying the de Rham functor is a vector bundle of the correct rank. which in terms of this functor RH plus amounts to the invariance under the connection, or rather flat sections, on the punctured disk to being of the correct rank. So rank of this over xk infinity could be the same as the rank of a local system. Okay. And you see that here, this condition will be satisfied for this connection if and only if a is an integer, right? Because that's when this connection will be algebraically trivial if you invert t. And which is consistent with the fact that this thing is drawn if and only if a is an integer. Okay. And let me introduce some notation for this, which I'll use later. I'll call it O of a. So it's a rank 1 module with this connection. This I'll call nabla. Okay. Right. So this is an example of how this works. Okay. So let me, now having set this up, the first part of the theorem follows by an essentially linear algebraic computation.
Yeah. The Riemann Hilbert, is it an algebraic variety or is it an analytic variety?
Here, this is for an algebraic variety, yeah. Somehow, it could be true that, as stated, this is also true for arbitrary rigid analytic varieties, though somehow the proof of a certainty completion result, which I have, uses quasi-compactness. So I use a compactification and use a quasi-compactness of that compactification. But this, maybe it's possible to remove. But the theorem itself crucially, it crucially uses the fact that you're an algebraic variety, in that it admits a compactification, in that it's Zariski dense in something proper. It's also true for smooth rigid analytic varieties which admit such a compactification, but even though I don't have a counterexample, the proof definitely doesn't work, say, for aphenoid variety. The Riemann-Hilbert correspondence might hold for a larger class of variety. Yeah, and by the way, as I stated, everything here is in the algebraic category. So it does take some work did by Diaolan, Liu, and Zhu to ensure that to kind of put an algebraic structure on the value of this Riemann-Hilbert. Okay, so yeah, the brief. Yeah, let's do it here. Oh, perhaps that can go too. Yeah, so suppose I start, let me just, to make things a little simpler, let me assume that my L is a QP local system. Such that if I extend the scale as to QP bar, it stays, its underlying geometric local system stays irreducible, such that L base change to extend scale as to QP bar over, when restricted to the geometric fundamental group, is irreducible. And I'm looking to find a character such that L tensor chi is the Rhamness. Yeah. So the question is, how can I possibly use this irreducibility property? So this functor RH plus is definitely not an equivalence. So it's not quite true that at least it's not quite obvious that the geometric irreducible objects go to objects with some kind of irreducibility. And anyway, this is irreducibility over K bar, not over. But you can say more about this functor, which I'll state as the following comparison theorem. And you should think of it as a p-adic comparison theorem because that's exactly what it is, but it's like a very special case of it. So for any L, what's true is that the endomorphisms of L over xk bar, well, the dimension of that is equal to the dimension over k infinity of t of the space of endomorphisms of the corresponding bundle, which are, I'll write it and I'll explain what this means, which are xk infinity flat. So it will mean that they're flat in the direction of x. So This is not a condition on T. So by definition, this is the algebra of endomorphisms which compute with all the local derivations in the x direction. So f commutes with nabla v for any v which is the local section of the tangent sheaf to x. Okay. So this is still a module over k infinity double brackets t. And well, this is really a p-adic comparison theorem. You should think of this as of de Rham cohomology because it's some flat sections, and this is zero vital cohomology. And there are versions of that for higher degrees. Okay. But now, if I know that my L is absolutely irreducible, I do know that this space is one-dimensional, right? By the Schur's lemma. So this dimension is 1. But now, it implies that this object RH plus of L should have no non-scalar endomorphisms which are xk infinity flat. So, in other words, this RH plus of L is sure irreducible. So it implies that RH plus of L, so it's kx infinity flat endomorphisms are only scalars. Sorry. Okay. So now I've got an object of this category such that it has no non-scalar endomorphism. But now all that remains is a purely algebraic analysis of objects of that category. So starting from this point, you can essentially forget about the Galois group. So it's a lemma which you can prove that if you have an object E in the category of vector bundles with a flat connection over xk infinity Laurent series T, so where I'm inverting T in that definition, such that it has no non-scalar. So here connection really means genuine connection. Since I've inverted T, I'm not allowing any further poles. So such that endomorphisms of E which are xk infinity flat are only scalars. Has the form a tensor product of a vector bundle E on xk infinity without the T, and one of those O of A's. So here E is a vector bundle with connection, with a flat connection on xk infinity, and well, O of A for some A in k infinity is just a one-dimensional module with the connection given by the same formula. Okay. So what's the reason for that? Well, what are vector bundles with a flat connection on this? Well, you can think of this topologically as of a trivial circle bundle on xk infinity. So its fundamental group is the product of the fundamental group of xk infinity and the fundamental group of the circle. So essentially, if you just say the same words in the de Rham setting, this comes down to separately studying vector bundles on xk infinity and vector bundles on the formal punctured disk. But it's easy to classify all of them. And you can prove that somehow the only objects which, so there are higher rank indecomposable objects, but they will all have non-trivial endomorphisms. So if you don't have non-trivial endomorphisms, you're forced to be a product of this with a rank 1 object. But now we win because by definition, by setup, we're allowed to twist away anything of rank 1. So this will be the last thing I'll say. So I'm going here. So I can find, so if I can find a character such that RH plus of that character is O of minus A, well, it requires a little bit more work of analyzing that, of proving that A actually lies in K, but let me kind of sweep this under the rug. Then L tensor chi will be de Rham because the result of applying this RH plus functor will be just a vector bundle pulled back from xk infinity. And so we win because that's what the theorem aimed to prove. Okay, so let me stop.
Thank you. Thank you for this enlightening lecture. So, any question in the room? Yeah.
My question is quite simple. So, if I understand correctly, the corresponding drum representation has a trivial Hodge state number. I mean,
trivial what?
Hodge state numbers are all 0, or?
Sorry, for this L?
Yeah, as this construction.
No, not necessarily. Well, this might
I
have like some sequence of Hodge state numbers.
But in your constructions, no log poles along T.
That's a great question. I've invoked T.
And
the Hodge state weights are the data of Hodge state weights is contained in the choice of a lattice.
I see.
Yeah, that's a very good question.
Just a naive question. Do you think something like Theorem 1 happens for Christian representation?
Yeah, that's a very good question. Somehow that would be contingent on proving some kind of global version of the potential of the Rhamness lying potentially semi-stable. Also, maybe a related thing is that there is a recent result of I think Elena No and Mikhail Groshning, where they proved that anything rigid is crystalline. Certainly an indication that something like that should be true. But yeah, I thought about this for a bit, but it feels like it should be true, but I don't have a proof. I mean, you should have some assumptions that maybe you have good reduction, for instance. That's a good question.
Other questions? So who is? Sorry.
Well, I have a question about the p-adic Riemann-Hilbert correspondence.
Please, yeah.
So in your statement, the RH plus functor is only feasible. And is there any natural condition on the vector bundle set you can add so that the RH plus is also full on the onto the subcategory?
Yeah, that's a really good question. It's not going to be something tautological because I'm forgetting a lot of structure. I'm forgetting that there should actually be a Frobenius on that bundle coming from, well, right, if I were to kind of enhance this to some kind of decrease, it definitely should be like a very non-trivial subcategory. Because, well, somehow, right, here, what I have on the source, like if you think about all space of representations of the geometric fundamental group, there I'm only picking local systems which extend to a finite extension of QP. It's something very sparse. Whereas on the right, I think like objects on the right probably have like positive dimensional moduli. So yeah, it should be something very non-trivial, but I don't have anything to say really about it.
Okay, so
I'm here. It's important. It's perfectoid, and well, if you were to choose another extension instead of the Sen operator, you would sort of have more data. So this Sen operator corresponds to the Lie algebra of the Galois group of that extension, and presumably there are versions of this where you may take larger Galois extensions and you would have more Sen operators. But yeah, I don't think this has been worked out in this setting. Yeah. Oh, well, E should also be like irreducible as a vector bundle. Sure, irreducible as a vector bundle on xk infinity. But I don't really even have to use any of that. Somehow, the source of problems is the action of the Sen operator, right? And we prove that it acts essentially by a scalar, which we can twist off. Yeah. So yeah, in this lemma, you can like add that E is sure irreducible.
okay, so if there are no other questions, and I think we should not forget Zoom. Yeah, no other questions on Zoom. So I remind you that we start at 5 and there is a cafe break just 30 minutes before. We have lunch now. So let's thank Sasha again.